Hey everybody, welcome to Chapter 2, Section 8. Title is Proportions and Similar Figures, starts on page 130. Now, the title says proportions, so we're going to use the same idea that we used yesterday with proportions, but in this case, we're going to use similar figures. So there's going to be a little bit of geometry in here today. It's going to be a little bit longer, so stick with me. A couple of definitions. Similar figures. This means that the two shapes, they have the same shape, but they're not the same size. And I'll have one of those down here at the bottom of the screen. In geometry, this little symbol, this little squiggly symbol, it's called a tilde. It means the word similar. So if I have that symbol, it means the two shapes are similar. They have the same shape, but they're not the same size. In geometry, angles are named by one capital letter. And sides are named by the two capital letters that are at the end of the side. So I've got some triangles down here. On the left, I have triangle ABC. On the right, I have triangle FGH. And then up here, I wrote their names. Okay, you name shapes in geometry. So I've got triangle ABC, similar to the little squiggly line, similar to triangle FGH. Okay, we'll talk more about that, what that similar idea means in a second. A couple things here. So right here, this would be angle A. Right here, this part of the triangle would be angle A. It's named by one capital letter. I'll just write that in here. Angle A. Okay. This side over here would be side AB. Okay? A side is named with two capital letters, the capital letters that are on each end of it. Okay? Over here, for example, that would be side FG. This would be angle H. Okay? So, the little squiggly sign means similar. Angles are named by one letter. Sides are named by two letters. Okay, just a little introduction for you. Here as well, too much. These are similar triangles up at the top. We can tell because of their names. Triangle ABC is similar to triangle DEF. Okay? I put some numbers in here as well. We'll get to those. In similar triangles, corresponding angles. The word corresponding means that they are in the same position. Corresponding angles are in the same position. So if we look for a second, angle A and angle D are corresponding because if I look at those two pictures, they're in the same place. There's another way that I can tell corresponding angles. Look at the names. In this triangle, angle A comes first. In this name, angle D comes first. So since they both come first, that means that they're in the same position in the names, which means that they are corresponding. Ask you a question. If I look angle C comes last in the name of this triangle. What angle is corresponding to it? What's in the same position? Well, C comes last in that name. F comes last in the second name. So C and F are both last, which means that they're corresponding. Look at the pictures and make sure. Angle C is here. Angle F is right here. They're both in the same spot in those triangles, so they're corresponding. Corresponding sides are also in the same position. Okay? For example, this side over here that's got the 8 on it, remember that would be side AB. If I look at the other triangle, the one that's in the same position, kind of top left, is side DE. So AB would be corresponding with DE. They're both in the same position. Okay, new idea. Corresponding angles are congruent, which means they have the same measure. So, This is a little bit more than you need, but the angles in the triangle add up to 180 degrees. So what this means is if angle A was 30 degrees, for example, the angle that is corresponding to it, which would be D, is also 30 degrees. If angle B was 90 degrees, then angle E would also be 90 degrees. Okay? The word congruent means same. It's kind of like the equal sign, but it's the geometry version of an equal sign. So, the way that we'd write this is angle A is congruent, which is an equal sign with a squiggly over it. Angle A is the same as which other angle did we say? Oh yeah, angle D right there, 30 degrees. Angle D. Those two angles go together. I could do the same thing. Angle B is congruent to angle E. They're in the same position. They have the same angle measure, same number there, 90 degrees. We didn't put numbers in it, but angle C would be congruent to angle F. They're in the same position. They have the same number value. Okay? So corresponding angles are congruent. Now, if we look at the sides are a little different. Corresponding sides can be used to make proportions. Okay, let's see what that is telling us. Okay. If I have corresponding sides, so let's say, okay, AB, that's side AB. What side is corresponding to AB? Well, if I look at my other triangle, DE is in the same position as AB. So we're going to write those two as a fraction. Okay. Let's look for another angle or another side in my left triangle. Let's say I have BC. Which side in the right-hand triangle is in the same location as BC? Well, it would be EF. Now, I can turn these four sides into a proportion. Okay? What that means is, if I would plug in these numbers, so AB is 8, DE is 12, and if I simplify that, I would get 2/3. Now, let's look at the fraction BC over EF. BC is 10, EF is 15, and if I simplify that fraction, I get 2/3. If my triangles are similar, all of the corresponding sides will end up simplifying to the same fraction. We'll see why that's useful when we do the next example problem. In the diagram, the two triangles are similar. What is AC? So we're trying to find this length right here. That's the missing length. Do we have two sides that have numbers that go together, that are corresponding? Well, 16 and 12. Aren't those two in the same position, kind of top right of the triangle? I can use that to create a proportion. So 16 goes along with 12. I write it in the same fraction. Okay? Now, do I have anything that matches up with 10? No, I don't. It would be right here, but I don't have anything there. So I'm not going to use the 10. The 10 is extra information that I don't need. But I am going to use the x and the 18. Now, the question is, do I put x on top and 18 on the bottom, or do I flip it over? Well, 16 came from the triangle on the left, and it's on top of my fraction. So the top of my fraction is always going to have to come from the triangle on the left. So that means that x is going to go on top. X and 16 both came from the same triangle, so they both go up on top. 12 and 18 both came from the same triangle, so they both go in the same position. They both go on bottom. Now that I've set up my proportion, I can solve it the same way I did in section 7, cross products. So I multiply 12 times x, I multiply 16 times 18. The equal sign stays in the middle. 16 times 18 is 288. My variable is being multiplied by 12, so I need to divide both sides by 12. And I get x equals 24. So the side that I was missing was AC, and we put an x there. That side is 24. That would be my answer. Next example, we can do this with kind of real-life type problems. A man who is 6 feet tall, that looks like a piece of information, is standing next to a flagpole. The shadow of the man is 3.5 feet. So the shadow is 3.5 feet. The shadow of the flagpole is 17.5 feet. We're trying to find what is the height of the flagpole. So there's 3 pieces of information we know, one that is missing. Now, you can see we're talking about 2 different things. We're talking about shadows, and we're talking about objects. Okay? So, just like in the last problem, we need to make sure that stuff goes in the right positions. So, let's say that over here, we're going to put the shadows, and over here we're going to put the objects. Okay? So the first shadow we're talking about, the shadow of the man, is 3.5 feet. Okay, that's the man's shadow. And the other shadow is the flagpole, 17.5 feet. Those are both shadows, so they go in the same fraction. The objects. Now, the 3.5 feet, that was from the man, right? Yep. Okay, so the man, the object, the man, is 6 feet tall. So since the man was on top of the left fraction, he has to stay on top of the right fraction also. The flagpole shadow is 17.5 feet. It was on the bottom, so the flagpole's object has to go on the bottom of the other one, and that's what we're trying to find. Set them equal to each other, and then we do cross products again. 3.5 times x. 17.5 times 6. Calculator. 17.5 times 6, 105. 3.5x equals 105. My variable is being multiplied by 3.5, so I need to divide by 3.5, and I get x equals 30. Now, word problem has units in it, so I need to make sure I put units in my answer. The height of the flagpole is 30, and the only unit we've got in this problem is feet. Now, I'd never be able to use a tape measure or a ruler in order to figure out that a flagpole is 30 feet. But if I can measure my height and my shadow and the flagpole shadow, I can calculate how tall that flagpole would be. Okay? Another type of problem, still using proportions, it's called a scale drawing. If you've ever used a map or something like that, you've used a scale drawing. A drawing that is similar to an actual object or place. Another example would be like a blueprint if you're building a building. The ratio of any length on the drawing to the actual length is always the same. So you're comparing the drawing to what's actually in real life. That ratio is called the scale of the drawing. It's important that when you have a scale problem, you always write the scale as its own fraction when you set up a proportion. Here's what I mean by that. The scale of a map is 1 inch to 110 miles. That is the scale. It tells it to me right here. So I immediately turned that into a fraction. 1 inch, 110 miles. That's half of my proportion. The distance between 2 cities on the map is about 0.6 inches. Now, I have inches on top of my one fraction. So what do you think is going to be on top of the other one? Inches again. Inches on top, inches on top. It says, what is the actual distance between the two cities? And what do you think that distance is going to be measured in? Well, over here I had miles, so over here I have to have miles. Now that I've set up my proportion, I can solve it using cross products. 1 times x is just x. 110 times 0.6. Grab my calculator. And I get that x equals 66, and remember that was in miles. So the distance between those two cities in real life is 66 miles. Okay. One more example, kind of like that. A scale model is a model that is similar to a real object. And the last time we had a drawing that was similar, now it's a model that is similar. If, for example, if you were going to create a scale model of the solar system, you couldn't build it the size that the solar system actually is. It would be too big. But you can make it so that all the distances between the planets and stuff are correct. That would be a scale model. The ratio of any length on the model to the length of the object is always the same, which means we can set up proportions. The ratio is called the scale of the model. In the last one, we set up the scale as its own fraction. The same thing is true here. If they give us a scale, we write it as a fraction. Here's your example. A scale model of a building is 6 inches tall. The scale of the model is 1 inch to 50 feet. So we write that as a fraction. 1 inch, 50 feet. Write it as a fraction. The other piece of information it gave us was 6 inches. Where do you think 6 inches is going to go? Well, it's on the top on the left fraction, so it has to be on the top on the right fraction. How tall is the actual building? That's what we're trying to find, and we're going to measure that in feet, because we have feet on the bottom of the left, we have to have feet on the bottom of the right. Now we use cross products. 1 times x is just x. 50 times 6 is 300, and we get x equals 300. Don't forget your units, feet. So that building is 300 feet tall. Use the problem, set up your proportions, make sure that your units go where they're supposed to, and then use cross products to solve your proportions. Practice problems for this section, there aren't many of them. 9 through 17 odds on page 134.